Well, hello again everybody. Now hopefully you'll remember in one of my previous videos I had rather a lacklustre attempt at cleaning my workshop out, and yeah, it didn't really end up any better. Basically I just got all my toys out and started playing with them. I think we're going to do that again today because I quite enjoyed it and I know some of you did as well. So I thought we could carry on and have a bit more of a look at some of the RF test gear that I've got. So we've got some RF dummy loads here. We've got attenuators, we've got spectrum analysers, we've got spectrum monitors, RF test sets.
So let's start by looking at transmitters and how to make some basic measurements.
I always say the best way to connect a transmitter to a piece of test gear is don't connect it. That's the best way. Now sat on this shelf here I've got my old Black Star frequency counter, and all I've got connected to it is a little loop of wire which is simply acting as an antenna. So if we want to have a look at the transmitted frequency on this radio, all we've got to do is got to key it up, and there we go, 145,587, 145,587. And of course we can do something very similar using our oscilloscope. So all you need to do is you take your oscilloscope probe, you take the ground lead and you connect it to the input side, the pointy bit, and as you can see you've got a little loop of wire, and what you've actually formed there is a loop antenna. Now this is a bit of an old engineer's trick that you quite often use for sniffing for RF currents and things on a circuit board. So if you've got maybe a source of interference or something on a PCB, this is certainly a trick that I was taught back in the day. So you make this little loop antenna and then you can actually just sweep it around various places in your RF circuit, and you can make RF measurements. Maybe you're looking for a clock signal or particularly on a radio, a local oscillator, but you might not want to directly connect your scope probe, because the problem with connecting scope probes is the effect, the measurement, the higher frequency, the worse that effect is. What you will get away with on a, I don't know, working at 7 megahertz, you won't get away at working at, I don't know, 150 megs or 200, or certainly not in the gigahertz range. But quite a nice non-intrusive test is just make a loop antenna like that. So here's the radio, key it up, and hopefully you can see on the scope there. And it's also quite interesting to see how directional everything is, which you don't always appreciate. Obviously it's more obvious in terms of what's happening with the signal using the oscilloscope than it is just a basic frequency counter. So what you're looking at there is our 145 megahertz carrier wave, and you can see as I bring the transmitter, the walkie-talkie, closer to the loop antenna we've formed in our scope probe, it gets bigger. And if I move it away, it gets smaller again. And we've already learnt quite a lot more about our signal there. There's one thing I can see by looking at that: it's nice and linear. You're not seeing any, it's not squared off at all. And whenever you're looking at transmitted signals, any kind of distortion on that lovely sine wave, that's something to worry about. But that's lovely, that's a lovely sine wave there, so that looks pretty good to me. Well, you can see in the background here I've just fired up my Marconi spectrum analyser, and I've got to admit I've got a bit of a love affair with this old girl. Now I think these were built in about the 80s. I've certainly owned this one for about the last 10 years, and when I actually purchased it I paid what I would say was quite a lot of money. It was certainly a lot of money for me at the time. It was £1,000, and I had to save up for, well, to be honest, it really took me a couple of years to afford to buy this, and I absolutely love it. It is my favourite piece of test gear in the shop. It's a beautiful thing, it is a thing of beauty. Anyway, sorry, maybe we should just get a room, eh? Well, we have done. Now this socket is the input to the spectrum analyser, and this type of plug arrangement, it's called an N-type connector. Now you might be more familiar with this type of connector, which is a BNC. Basically, if you're working at high frequencies, you will need to use N-style connectors. If you're working at lower frequencies, BNCs are generally fine. Now a little bit of a top tip for you here. What you should do is, if you've got a spectrum analyser, it makes a good idea to buy a good quality adapter and screw it on. And the reason that I recommend you do that is because you're constantly going to be plugging things into here, unplugging it, all different types of equipment. And what you can do is, if you can wear out the connectors You don't want to do that because they are very expensive, stroke impossible to repair. So if you actually just screw on a BNC adapter like this, it's kind of sacrificial. If anything ever damages this, it's fine. Well, I heard a story just the other day about an RF test lab where they had some really, really expensive test equipment. They were using something called vector network analysers, really expensive bits of kit, maybe, I don't know, anywhere between 20 and £100,000 worth. And what they found had happened is that they started having problems with all their RF test gear. And what it turned out to be is, after a lot of searching, is they found a test lead, and the test lead was damaged inside, and this test lead had gone all around the company and been plugged into different pieces of test gear, and it had damaged the connectors and all the VNAs, and yeah, it cost them many tens of thousands of pounds to repair. So if you put on an adapter like this, it's sacrificial. One thing I would warn you against though is, perhaps don't just buy your adapters off eBay. Go to a good source, I don't know, RS Components, DigiKey, somewhere traceable, because if you just buy these things on eBay, you don't know the quality of the manufacturing, and you know, it would be actually quite easy if one of these connectors was incorrectly machined or something like that and you screwed it in there, it could damage the socket. So just be really, really careful with your connectors on RF test gear. So I've just taken that little wire antenna off the frequency counter. I'm just going to stick it on the input of this spectrum analyzer. And this time when we key up the transmitter, you can see the waveform, and it works just the same as before. If I move the transmitter closer to the input, closer to the aerial, you can see that the signal strength is going up. If I move it away, it falls again. Closer, goes back up, and far away. Well, so far so good. We've just made some RF tests and measurements there. We've had a look at the output from our transmitter on the oscilloscope. We've seen that it's a nice output sinusoidal waveform. It's not squared off, so it's not going to be generated. Oh, Jesus. Well, it was genuinely quite frightening when that spectrum analyzer blew up behind me. It was quite a loud bang, and yeah, it was just in my ear. You saw me jump, didn't you? So I definitely feel a little bit put out, a bit perturbed at the moment. But yeah, we'll carry on. These things happen. It's funny, I was only talking to the DEFPON the other day, to Scott, and we were just talking about X-rated capacitors wired across the mains, and I'm hoping it's going to be something simple like an X-rated capacitor, although quite often, as we were saying, that you can normally smell when they go bad. I can't smell anything, but I'm not investigating today, but I think whatever has gone wrong, it's a very hard short across the mains. It's taken out not just the fuse in the plug of the spectrum analyzer, it's actually taken out the fuse in the extension lead as well, and the fuse is all just moltenized, metallized on the inside, so you can always tell when it goes like that. It's not a steady overload, it's been a really hard short. So, you know, maybe I'll get lucky and it's just a simple fault, but yeah, I'm going to be a bit of a big girl's blouse. It was a bit frightening, that. So I'm going to drink some tea and calm my nerves. So apologise if this video's a little bit disjointed. I'm not sure where we got to with that. So the first problem at hand we've got is we have to make a physical connection now to this output socket on this radio, and I think that this is some form of a TNC connector. It's threaded, so we've got to find a suitable adapter which will screw into the radio, and I think I've happened to have one here. Yeah, I'm not exactly sure what they call that connector. I don't know if it is a miniature TNC. I'm sure there's a correct name. I'm not sure what it is, but it's not a BNC. But that connection's quite important, and before I did mention about needing various RF adapters, so let's have a look at some of them. So you look at this box here, which is absolutely full of all types of different adapters, and you'll be glad to know you don't have to go away and buy all these at once. This is come from 20 years of me working on various types of radio equipment, and I've bought these adapters as and when I've needed them. So I've taken out one of my most used adapters, and this is an N-type to BNC adapter. I find that I use a lot of N-type cables and a lot of BNC type cables, and the input on your spectrum analyzer will almost certainly be an N-type connector. Now, I mentioned earlier that in terms of frequency range, the N-type, this type of connector, is far superior to the BNC, but in the real world I tend not to worry about it. It doesn't make a lot of difference for what I do. There's a lot of advantages to BNCs, and I guess the main advantage is that the cables are cheap, the connectors are cheap, and they're very quick and easy to assemble because it's just a bayonet connector. In fact, we've got one here. It's much easier to just to plug one of these in like that, job done, as opposed to getting an N-type connector and having to assemble it. So, you know, let me see if I can find an N-type female, sorry. So this is a right-angled N-type adapter, and yeah, it's a right-angle shape, so it's got male on one side, female on the other, and basically this just screws together. And that's not a big job. You can screw it together, but it's not as easy as doing that, is it? So that's why I use BNCs. Also, BNC cables are a lot cheaper. Well, let's have a look at some of the other adapters. But that's certainly one that you're going to need a lot of. You're going to need N-type to BNC. So this adapter here is a PL259 connector, and this is the kind of connector you're going to find on the back of your CB radio or your amateur radio transmitter on the low frequency range. The high frequency range you're going to find a BNC or an N-type, but for the low frequency range you're quite likely to find PL259. So what this is, it's a PL259 to N-type adapter, so that's one you're going to commonly use quite a lot. And once you've got these, you can do things like you can screw the adapters together. So now I'm going to convert PL259 to N-type, and then I'm converting it back to a BNC. That took a bit of screwing together, that. You can see why I don't always use N-types. Okay, so I've got out another of the adapters, and this one is called a TNC, and a TNC connector is it's a lot like a BNC, but rather than being a bayonet fitting, it has a screw thread on it. So you actually screw these on the types of places you might find a TNC is. I think a lot of your video cables, you know, coming down from your satellite, your LNB. I think quite a lot of them plug into the box on things like TNC connectors. So I've heard anyway. I've never used them for that application, but quite a lot of radio equipment in the VHF range and above will use TNC. Well, you can shut up. Now, we saw earlier that if we just had an antenna connected to the radio and to the spectrum analyzer, although we could look at the frequency and the amplitude, it wasn't really practical in any way to actually do real power measurements. It would be subject to the frequency we were transmitting at and how we held the transmitter and all things to do with characteristics of the antenna. You can't do an accurate power measurement like that. So you've got to do a direct connection. So what we're going to do to just demonstrate that is we're actually going to use one of these absorption watt meters, and we featured this one last time. It's made by Ray Caldana. Is there a model number on it? Oh yeah, it's a model 9102, and these are quite a popular unit. There was a lot of these made, and you can still find them second hand, but they do go for quite good money now, this stuff, because it was very well made. Now, the input to this watt meter uses an N-type connector, as we've just been talking about, but our transmitter has now got a lead on it with a BNC, so we're going to use another adapter. Now, when you're carrying out any type of RF measurement, where possible, you want to keep all these connecting leads and the number of adapters to an absolute minimum. You want to keep all the cables as short as possible, and you want to use the fewest amount of adapters that are possible as well. Again, at low frequency, you know, maybe up to 100 megahertz, really doesn't make a lot of difference. But at high frequencies, the adapters can make all the difference in the world. So let's switch this radio on and let's actually take a power measurement.
Frequency mode.
So we've got a selector switch on the side of here, and it's got a 30 watt and a 10 watt connection. So we'll put it on the 10 watt connection, and we'll just key up the transmitter. So it looks like even though we've got this little handheld transceiver set to low power, it's actually outputting about What's that? Would you say that's about 1.7, maybe 1.8 watts? We're just looking at the top scale at the moment. So we can modify the output power on this transceiver. Let's just do that. TX power low. Let's just put it to high. So now when we key it up, just under 6 watts. There tends to be an awful lot of variance in these Baofeng radios. Some of them hardly transmit anything. You know, you're lucky if you get 4 watts out of them, and as you can see, this one is doing just under 6. So yeah, it must be a fine example of the beast, this one. Fine example of the breed, sorry. Now of course there's some big advantage to having this cable connection. Firstly, it doesn't matter how we orientate the radio to the piece of test equipment, the output power doesn't vary. See, I'm wiggling it around, but the needle's not moving. When we were doing that with just the antenna, the power was going up and down. So that's a big advantage. The other big advantage is we're now not broadcasting to the rest of the world, because all the power coming out of the transmitter there is going into this watt meter and absorption watt meter. It's being absorbed because at the front of here there's an RF dummy load, and we'll talk about dummy loads maybe a bit more. So all the power is going out of the dummy load, it's going into a big resistor here, and that power is being dissipated as heat. So it's not being dissipated as RF radiation in the atmosphere, it's being dissipated as heat. And I can prove that. So here's a radio receiver, and it's set to exactly the same frequency as the transmitter. So let's just put it down there and turn the volume up full so you can tell, show I'm not lying. Let's rest it on there and we'll key it up. And you can see this radio is not doing a sausage, it's not receiving anything. So we're not radiating any signal into the outside world. So let's just double prove that. So quite quickly, we've just done quite a few little tests there. We've had a look at the signal on the oscilloscope. We've had a look at it on the spectrum analyzer, and we've seen that the waveform looks undistorted. And we've also done a power measurement. So we've done quite a lot of basic tests there to, you know, determine the health of our little transmitter. By all means, we haven't done all the tests we should do, but we've done some of them. But as you can see, this is quite a low powered transmitter. The maximum was only 6 watts. Things start to get more difficult as the power of the transmitters go up. So let's look at some bigger transmitters. Now what I've got set up on the bench here is a Yaesu FT897. These are a very, very popular amateur radio transceiver, and yeah, manufactured by Yaesu. Now under the conditions of the radio transmitting license, there is various things which are stipulated, which are things like the frequency you can use and the output power. And you've also got things like topics of conversation. Now of course in the UK you're only allowed to talk about 2 things, which one is you're allowed to talk about Land Rover gearboxes and the various springs that fall out of them, and the other topic of conversation is the weather, and you're not allowed to talk about anything else. You've got other rules for different parts of the world. For example, if you're in Italy, part of the licensing requirements are that all the transmitters that you operate must be more than 1,000 watts. So obviously this type of equipment would be outlawed in Italy because it can be turned down to 5 watts. So you can see on the back of this radio it's actually got 2 output connectors. You've got a PL259 and you've got an N-type connector. So it uses the N-type connector for the high frequency band. So 144 megahertz and above, it uses this N-type. But for low frequency, which is anything under 50 megahertz for this, it uses the PL259. Now I think what we'll actually do is we will actually use the PL259 connector, and we'll use it at you know, at the low frequency, the medium frequency range, and we'll do that because it can actually output more power. At the lower frequencies this can output up to 100 watts, so yeah, let's use it in the 100 watt range. So on the output from here we're going to need to use the PL259 lead, so we'll screw that in. And then on the other side we're going to have to find an adapter to go between 259 and the N-type. So you can really see why you're going to need to start to collect various types of these radio adapters, because well, whatever you have, you never have the one you want. It's you know, it's that sod's law thing. So there we are at 10 watts, 20, and that's about 30 watts. It's showing a bit less than that on here, but I'll keep going. 35 watts, and this is showing about 30 watts. So all the RF energy now is being absorbed by the big resistor in here, and it's being dissipated as heat. But I can't go any further. I can't continue to increase my output power, because at some point I'm going to probably damage this watt meter. So we've got a few choices for higher power measurements. So I've just been rummaging around underneath the bench, and I've just found this bigger watt meter. It's basically just got a bigger dummy load, and this one will actually go up to 200 watts. So let's just increase the power. So where we are, about 30. So let's go about 50. Right, 100 watts. This is showing about 90. I don't know where the inaccuracy is. It could be in the meter, could be in the transmitter, I don't know. That's not untypical, 90 watts. So that takes us so far, but there's a limit to how big a dummy load and how big a watt meter we can use. So what other choices have we got? Well, what we need to do is reduce the output power to the transmitter to something more reasonable. And the way that we do that, or one way we can do it, is to use attenuators, which are basically just big resistors that we can use to drop the power. Well, before I talk about attenuators, I probably need to take a step back and talk a little bit about dummy loads, because I've really not explained that properly, have I? So this is our transmitter, and when we're transmitting, lots of RF energy gets squirted out of the connector at the back. It runs down the wire, and normally it comes out of your antenna on the roof, or the long wire outside your house, or whatever you've got. It goes into your antenna and gets transmitted. But we said there's a problem with that, in that when we're doing testing, we don't want to be radiating all the RF energy and disturbing all our neighbours with our noisy, dirty transmissions. So what we have to do is we have to use a piece of equipment. Instead of an antenna, we use what they call a dummy load. And what the dummy load does is it converts all that RF energy, and it actually just effectively wastes it. It converts it into heat. The only thing you've got in here is a big resistor, and all the RF energy goes in there. It gets converted to heat where it's harmless and it doesn't annoy anybody. That's only half the story though, because normally the transceiver is designed to be connected to an antenna, and that antenna in a perfect world will be tuned, and it will present a known impedance, a known resistance to the actual transceiver. And for most transmitters and receivers in use today, it'll probably be 50 ohms. Historically, for TVs and stuff like that, it would have been 75 ohms. For audio gear, I think, don't they use hundreds of ohms? I'm not exactly sure, but typically most RF transmitters today will be 50 ohms. So the other thing that the dummy load needs to do, it needs to look like a 50 ohm resistor, and the reason it needs to look like a 50 ohm resistor is because if it doesn't look like 50 ohms, for example, if we have this disconnected from the load, what will happen is all the RF energy will come running down the wire. And you would think because it's not connected, it just shoots out the end. Well, it doesn't actually just shoot out the end. Some of it will leak out. But what tends to happen, because this isn't 50 ohms, it's a different impedance than what the cable is. So the RF energy comes shooting down, and it's like it hits a brick wall, and that energy will get reflected back down the cable. It gets reflected back down, and it'll run back down here into our transceiver and possibly blow up the output stage. So the other thing that the dummy load does, it presents a known impedance to our transmitter. So I went all around the houses to explain that, didn't I? Oh well, I always do that, don't I? Now when it comes to dummy loads, size really matters, and according to my wife, big is better. So you can see that this one is 150 watts. So this will run with our 100 watt transceiver, absorbing all that energy. It will do that all day. Whereas these small ones would very quickly get hot and overheat and probably burn out. The resistors in them would burn out. So when you're purchasing dummy loads, it's worth remembering that a big dummy load will do everything that a small one will do, but a small dummy load won't do everything that a big one will do. So yeah, buy the biggest you can. So here's an attenuator, and here's a dummy load, and you can spot some differences. Most strikingly probably is that the attenuator has got two connectors on it, whereas our dummy load has got one. Of course, the reason for those two connectors is that the power in an attenuator has to go through it, and the job of an attenuator is to reduce that power. So this one is a 10 dB attenuator, so it will reduce the power by 10. I've got a different one here. This one is find the label. This one is a 20 dB attenuator. So if we put power through it, it will reduce that power by 20 dBs, or divide by 100. And we've got a big buffer here, and this is a Tenuline attenuator, quite a good one actually. It's filled with oil to dissipate all the power, and this one is 30 dBs. So if you transmit power through here, you'll put the power in at one side, and what comes out at the other side, the output, will be 1/1000th of the power. And it's quite important that to remember, not all attenuators, but certainly a lot of them are directional, and if you plug them in the wrong way around, you'll blow them up. So let's plug in this -3 dB attenuator and give it a try. So remember, this is -3 dB, so that's going to reduce the power by half. So we've got the transmitter connected without the attenuator now, and we've got it set to 10 watts, and the needle is pegging at 10 watts. So let's install our attenuator now, and if we've got it right, the power should now be half because it's 3 dB, and we should just see 5 watts on our meter. So we'll key up our transmitter with our 3 dB attenuator connected, and we should see 5 watts. And there we go, we're looking at the top scale, so that's 5 watts. We're transmitting 10 from the output of the transceiver, and the attenuator is attenuating 5 watts of that away, leaving the power meter with 5 watts to display. So the attenuator has reduced the power, it's reduced it by half. Now I'm afraid I've done quite a lot of talking today, and taken a very surreptitious wandering journey, but where we started was that I wanted to try to explain maybe how you would be able to connect something like a transmitter to the inputs of a spectrum analyzer. So, and what I said was that the input to your spectrum analyzer can be very easily damaged by high input signals. So what we need to do is we need to reduce that to a level that the spectrum analyzer can cope with without damage or overloading the front end. Because that's the other thing, even if you don't damage the input to your spectrum analyzer, if you just put too much power into it, you'll get totally misleading readings. The amplifier in the front end won't be acting in a linear way, and you'll just get a horrible distorted output from your spectrum analyzer. The input levels are really important on these instruments. So where we've really got to it is the output from your transmitter has got far too much power. You're going to damage the input to your spectrum analyzer. We need to reduce it. One way that we can reduce it is by using attenuators. So let's do that. Let's use an attenuator to reduce the power, and then feed that into one of our spectrum analyzers. Yeah, but not the Marconi one. So before we destroy another spectrum analyzer, let's just double check ourselves. So we've got a transmitter here. So here's our transmitter, our TX, and we've got this set to 100 watts. Now, it's quite a good idea to work in something called dBm, but talking about dBm is a little bit outside of today's video, so I'm not going to. But what I'm going to tell you is 100 watts. Another way to say 100 watts is to say it's 50 dBm. And what that means is I'm referencing it to a 1 milliwatt signal, and maybe we'll get into that another time. So we've got a 100 watt transmitter. That 100 watt transmitter is going to go into this big through line attenuator, and that is minus 30 dBs. And then on the front of that through line attenuator, we're going to bolt another attenuator, which is minus 10 dBs. And then finally we're going to have our spectrum analyzer, which is going to show our wave. And the great thing about working in dBm is we can kind of do some quick and dirty tricks. We're going to have a 50 dBm signal, minus 30, minus 40, let's call that minus 40. So the thing about dBs is we can add them up. So 50 plus minus 40 equals 10 dBm. So if we've got everything right, when we key up our transmitter, our spectrum analyzer number 1 shouldn't explode, and our signal level there should be minus 10 dBm for a 100 watts or plus 50 dBm input. Fingers crossed, eh? 100 watt transmitter plus 50 dBm, minus 40 dB of attenuation. Spectrum analyzer. 1, 2, 3, easy wizzy, let's get busy. And if we look at the marker that I've set up here, it's actually saying that our signal level is 9.5, and what did I say? I said 10. So we're in the realms of error there. Thank God that didn't blow up. Now, the whole purpose of making this video was actually to talk about directional couplers, and we didn't get to do that today, so hopefully we'll do that again in the future very soon. So that's something we can have a look at. And all the attenuators that we looked at today, if I reach back, these are all fixed attenuators. They come out of the factory and they are set to whatever they're set to, you can't change them. But there's different types of attenuators as well. There is some which are variable. So here's a variable attenuator. You can set how much attenuation you want. Here's a different design of it. It has these 2 control rings and a front one. And then I've got yet another one here. So maybe next time, if anybody's interested, we can have a look at these attenuators, and we can also have a look at things like spectrum monitors and communication analysers. If you find this interesting and you want to see more, leave it in your comments. If you think I'm an idiot, leave it in the comments. If you think I've done something wrong and I can improve, leave it in your comments. It's all good. If you enjoyed this video, please like and subscribe, and I hope to see you again very soon. But until next time, that'll do. Bye for now.